If you could shrink yourself down to the size of an atom, or expand yourself until entire galaxies looked like grains of sand, you would quickly realize that the universe has no obligation to make sense to you. We spent centuries building what we thought were the ultimate rules of reality. We have Newton's laws for the motion of planets, Einstein's relativity for the fabric of space and time, and quantum mechanics for the tiny world of particles. But out there, in the deep silence of the cosmos, there are things that look at our physics textbooks and treat them like mere suggestions. There are objects moving faster than the speed of light should allow, particles that exist in two places at once, and structures so massive they shouldn't have had time to form since the beginning of existence. Today, we are diving into 10 things in space that completely break the laws of physics as we know them. And they suggest that everything we think we know might just be a tiny piece of a much stranger story. First on our list is something that fundamentally challenges the speed limit of the universe: superluminal motion. We've all been told that nothing can travel faster than the speed of light. It's the ultimate cosmic law. If you break it, causality falls apart, and time starts moving backward. But when astronomers pointed their radio telescopes at certain distant quasars and active galactic nuclei, they saw something impossible. They observed jets of plasma appearing to move at speeds 5, 10, or even 20 times the speed of light. Now, the official scientific explanation is that this is an optical illusion caused by the angle at which the material is traveling toward Earth. It's called a projection effect. However, some researchers argue that the sheer consistency and scale of these observations push our geometric explanations to their limit. Even if it is an illusion, it highlights a terrifying reality. Our eyes and our instruments can behold things that flat out contradict the most basic rule of Einstein's universe. It forces us to ask if we truly understand the relationship between distance, time, and velocity when we look across billions of light years. Next, we have to talk about the black hole information paradox. This is arguably the greatest fight in the history of physics, hitting Stephen Hawking against the entire field of quantum mechanics. According to the laws of quantum physics, information can never be truly deleted. If you burn a book, you could technically reconstruct the text if you could track every single atom and photon of smoke and ash. Information is preserved. But then along comes a black hole. When something falls into a black hole, it's gone. And when that black hole eventually evaporates over trillions of years through Hawking radiation, that information appears to be gone forever. This breaks the law of unitarity, a cornerstone of how we understand the subatomic world. If a black hole can truly erase information, then the laws of physics aren't constant. They can be destroyed. Scientists have been scrambling for decades to find a firewall or a holographic principle to save the information. But so far, the black hole remains a giant cosmic shredder that refuses to follow the rules of quantum bookkeeping. Third on our list is a structure that is simply too big to exist. It's called the Hercules Corona Borealis Great Wall. In modern cosmology, we have something called the cosmological principle. It states that on a large enough scale, the universe should look the same in every direction. It's supposed to be a smooth, even distribution of galaxies. Our math says that no single structure should be larger than about 1.2 billion light-years. But the Hercules Corona Borealis Great Wall is a massive filament of galaxies that stretches for over 10 billion light-years. That is more than 10% of the diameter of the entire observable universe. It shouldn't be there. There hasn't been enough time since the Big Bang for gravity to pull that much matter together into a single organized structure. Its existence tells us that either the universe is much older than we think, or gravity works in a way that we haven't yet discovered. It breaks the smoothness of the universe and suggests that the cosmos is way more lumpy and disorganized than our theories allow. Moving into the realm of the tiny but mighty, let's talk about quantum entanglement, famously described by Einstein as spooky action at a distance. Imagine you have two electrons that are entangled. You keep one on Earth and send the other to the opposite side of the galaxy. If you measure the spin of the one on Earth, the one on the other side of the galaxy instantly settles into the opposite spin, not after a few years, which is how long light would take to travel that distance, but instantly. This seems to break the law of local realism and the universal speed limit. How does the second particle know what happened to the first one across 80,000 light-years of space? While physicists argue that no information is being sent because we can't use it to send a text message, the physical reality is clear. The particles are connected by something that operates outside of three-dimensional space and time. It breaks our concept of distance entirely. Number 5 is the magnetar. These are a type of neutron star with the strongest magnetic fields in the universe. A magnetar's field is 1,000 trillion times stronger than Earth's. This is so powerful that it actually breaks the chemistry of atoms. If you were to get within 1,000 kilometers of a magnetar, the magnetic force would be so intense that it would stretch the atoms in your body into long, thin, needle-like shapes. Your molecular chemistry would simply stop working because the electrons would no longer be able to orbit the nuclei in the ways the laws of physics dictate. Light itself, when passing through this field, gets polarized and split in a process called vacuum birefringence. In the vicinity of a magnetar, the vacuum of space itself acts like a physical prism. It's a place where the standard laws of electromagnetism are pushed into a non-linear regime, where the math we use for every other part of the universe simply breaks down. Then there is the oh my god particle. Back in 1991, a detector in Utah picked up a single cosmic ray, likely a proton, that was traveling at 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999 of the speed of light. This single subatomic particle had the kinetic energy of a fast-pitch baseball. According to the laws of physics, there is something called the GZK cutoff. This is a speed limit for cosmic rays because, at such high energies, they should interact with the background radiation of the Big Bang and lose energy. No particle should be able to travel across deep space with that much juice. Yet, we detected it. We have no idea what could possibly accelerate a single proton to that level of energy. It would require a particle accelerator millions of times more powerful than anything we can build. It defies our understanding of natural acceleration and the limits of particle energy. Next on the list is the Pioneer anomaly. This one is a bit closer to home. When we sent the Pioneer 10 and 11 spacecraft out toward the edge of the solar system, we noticed something strange. They weren't where they were supposed to be. Both spacecraft were experiencing a tiny, mysterious force that was pushing them back toward the sun, causing them to slow down ever so slightly. For years, scientists couldn't explain it. Was it a new law of gravity? Was it dark matter? Eventually, they realized it was likely due to the thermal recoil of the spacecraft's own heat hitting its antenna. But even with that explanation, the math doesn't perfectly align for many researchers. The anomaly sparked a massive re-evaluation of how we measure gravity in the outer solar system. It showed us that even our most precise calculations of motion can be thrown off by the tiniest. Number 8 is the mystery of the second law of thermodynamics and the beginning of the universe. The second law says that entropy, or disorder, always increases. This is why eggs don't uncrack and why your room gets messy but never cleans itself spontaneously. This means the universe started in a state of extremely low entropy. It was perfectly organized. But according to the laws of probability, a low entropy state is incredibly unlikely. It's like tossing a billion coins and having every single one of them land on heads. Physics doesn't explain why the Big Bang was so organized. If the universe is a random event, it should have started as a disorganized mess. The fact that the laws of physics started with such a glitch of perfect order is something that keeps cosmologists up at night. It suggests there was a reason or a mechanism for the beginning that lies completely outside our current understanding of probability and time. Then we have dark energy. We know the universe is expanding, but we discovered in the late 90s that the expansion is actually accelerating. Something is pushing the galaxies apart faster and faster every second. In physics, if you want something to accelerate, you need to add energy. But where is this energy coming from? It seems to be coming from the vacuum of space itself. As the universe expands, there is more space, which means there is more dark energy, which means it expands even faster. This seems to break the law of conservation of energy. It's as if you have a car that gains more fuel the more you drive it. Dark energy makes up 68% of the universe, yet it doesn't fit into our standard model of particles. It is a constant, invisible force that behaves unlike any other field we have ever measured. Finally, we have the singularity at the center of a black hole. This is the ultimate physics breaker. At the center of a black hole, our math says that a massive amount of matter is crushed into a point of zero volume and infinite density. In physics, infinite is usually a code word for our theory is broken. When we try to apply general relativity to a singularity, the numbers go haywire. When we try to apply quantum mechanics, they also go haywire because the gravity is too strong. The singularity represents the place where the laws of nature as we know them simply cease to exist. It is a hole in the fabric of the universe where time stops and space becomes meaningless. It is the final frontier, a place that reminds us that our current laws are really just approximations that work in most places, but fail at the most critical points. The reason these 10 things are so important is that they remind us that science is not a finished book. We are like people trying to figure out the rules of a game of chess by only looking at one corner of the board. We see the knight move in an L shape and we say, that is the law. But then we see a pawn reach the other side and turn into a queen, and we realize our law was incomplete. Space is full of these pawn-to-queen moments. Every time we find something that breaks the laws of physics, we are actually finding a clue to a deeper, more beautiful set of rules. Think about the implications of the Hercules Corona Borealis Great Wall. If the universe isn't smooth on a large scale, it means our standard model of cosmology has a blind spot. It means the way matter clumped together in the early seconds of the Big Bang was influenced by forces we haven't named yet. It moves us away from a simple explosion model and towards something much more complex and intricate. And perhaps gravity isn't the only thing shaping the universe. Perhaps there are long-range forces or topological defects in the fabric of space that act like cosmic scaffolding. And what about the oh my god particle? If a single proton can carry that much energy, it could be a spinning black hole's magnetic field or a shockwave from a colliding galaxy. By studying these particles, we are looking at the output of the most powerful machines in existence. Even the Pioneer anomaly, though partially explained, warns us about our assumptions. We calculate the paths of planets and probes based on the idea that gravity is a constant, unchanging force. But what if it isn't? What if gravity changes slightly over massive distances or in different parts of the galaxy? This is the basis for theories like MOND, or modified Newtonian dynamics. These scientists suggest that we don't need dark matter at all if we just admit that gravity doesn't work the same way in the suburbs of a galaxy as it does in our own backyard. The mystery of dark energy is perhaps the most humbling. We spend centuries trying to understand stuff, atoms, stars, planets. Now we realize that stuff is only a tiny fraction of the universe. Most of existence is made of a dark energy that we can't see, touch, or explain. It's like we've been studying the white foam on top of a wave, and we're only just realizing that there is an entire ocean beneath it. Dark energy represents a fundamental property of space itself that we are just beginning to glimpse. If the laws of physics can be broken at the center of a black hole or in the flickering light of a distant quasar, what does that mean for us? It means we are part of a reality that is far more flexible and far more mysterious than we ever dared to dream. We are living in a time when the impossible is being observed every day. We are seeing the light from the first stars. We are hearing the ripples in space-time from colliding black holes, and we are measuring the spooky behavior of particles. This is why people are so drawn to space. It isn't just about the pretty pictures or the big numbers. It's about the feeling that we are on the verge of a massive breakthrough. Every time a new telescope goes up or a new particle is detected, we are looking for the glitch that will reveal the next layer of the universe. We want the laws to break, because that's where the truth is hiding. A universe that made perfect sense would be a boring one. A universe that defies our logic is a universe that has more to teach us. As you look up at the stars, remember that you are looking at a giant laboratory where the rules are constantly being tested. Those points of light are the sites of nuclear fusion that would baffle ancient scientists. The dark spaces between them are filled with energy that defies our current chemistry. And the distant galaxies are part of a structure so large it challenges our sense of time. We are tiny, yes, but we are also the creatures who have started to notice the cracks in the sky. Each of these physics-breaking discoveries is an invitation to think bigger. We need to rethink how information is stored, how energy is conserved, and how distance is measured. We are moving toward a theory of everything, but to get there, we have to be willing to let go of the theory of some things that we've been clinging to. We have to be brave enough to admit that the universe is not obligated to follow the rules we wrote for it. The oh my god particle, the Great Wall of Galaxies, the singularity. These are the landmarks of the new frontier. They are the spots on the map that say, here be monsters. But in science, monsters are just the things we haven't named yet. By chasing these anomalies, we are expanding the reaches of human thought. We are learning to speak the language of the cosmos, even if that language seems to contradict itself sometimes. We are also learning that the universe is incredibly resilient. It can house structures that shouldn't exist and particles that move too fast, yet it all holds together in a beautiful, grand design. There is a logic to the chaos, even if it's a logic we aren't smart enough to understand yet. That is the beauty of the pursuit. We don't want the answers handed to us. We want to earn them by looking at the things that don't make sense and asking why. The next century of space exploration will be defined by these questions. We will use gravity wave detectors to listen to the moments just after the Big Bang, to understand that low entropy glitch. We will use the James Webb Space Telescope to look at the first galaxies and see if gravity was working differently back then. We will develop new quantum computers that might finally explain how entanglement works across the void. And perhaps, one day, we will find a way to peer inside a black hole without the math breaking down. Until then, these mysteries remain the most exciting things in existence. They are the proof that we still have so much to learn. They keep us humble, they keep us curious, and they keep us looking up. The universe is a vast, challenging, and rule-breaking playground, and we are just starting to learn how to play the game. When you think about the laws of physics, don't think of them as stone tablets that can never be changed. Think of them as a map. And like all maps, the closer you look, the more detail you find. Eventually, you find a place where the map ends, a place where the ink runs out and the paper is blank. That's where these 10 things live. They are the things beyond the edge of the map, and for a species of explorers, there is no better place to be. The stories of space are often told in terms of what we have found, but the best stories are told in terms of what we haven't figured out. The physics breakers are the protagonists of our modern scientific epic. They are the rebels of the cosmos, refusing to fit into our nice, neat boxes. They challenge our ego and inspire our imagination. They remind us that for all our technology and all our brilliance, we are still just children sitting on the shore of a vast and mysterious ocean. So the next time you hear about a discovery that changes everything, don't be surprised. The universe has been changing everything since the beginning. It has been breaking its own rules and inventing new ones for billions of years. We are just the lucky ones who get to watch the show. We get to witness the dance of the magnetars, the flight of the ultra-high energy particles, and the expansion of the dark void. The laws of physics are the best tools we have for now, but they are not the end of the story. The end of the story is still billions of light years away and trillions of years in the future. In the meantime, we will keep looking at the things that don't make sense, because that is where the real magic happens. In the anomalies, in the paradoxes, and in the impossible structures of the deep, we find the true face of the universe. And it is much more beautiful than any textbook could ever describe. The universe is not just stranger than we imagine, as the famous saying goes. It is stranger than we can imagine. And those glitches in the laws of physics are the proof. They are the whispers of a deeper reality, waiting for us to finally understand the words. As we continue our journey among the stars, we should embrace the unexplained. We should welcome the contradictions. Because in a universe as grand as this, the most exciting word a scientist can hear isn't eureka, it's "that's weird." Because that's weird is how the world changes. It's how we move from fire to electricity, and from horses to space stations. It's how we will move from our current understanding of the world to whatever comes next. The things that break the laws of physics today are the foundations of the physics of tomorrow. We are just in the messy middle of the rewrite. And honestly, there's no place more exciting to be. Keep asking the big questions. Keep looking at the things that shouldn't be there, and keep wondering. The universe is waiting to be understood, and it has plenty more laws to break before we're done.